Hello, it's Keith here, and this is lesson 23 of the simple series of my Z80 assembly programming tutorials. Now, last time we were looking at sprite clipping, and today we're still looking at sprite clipping on the Amstrad CPC. However, we're going to go into some more detail this time on how this routine has been enhanced to make it faster on this particular system. Now, the enhancements in question are the use of so-called stack misuse. This is where we use the stack pointer instead of as a temporary store. We use it for fast reading or writing of data. So this is a trick that you can use if you are looking to make your games as fast as possible. It's a little bit difficult though, so it's not really a beginner thing, but definitely worth considering as you start to write your game and as you want to try and optimize your game to the maximum extent. So this is being used to clear the screen and also to read the sprite data. Now, because a push and a pop command on the Amstrad CPC, the Z80, use 16 bits. This means we're working in pairs of bytes, and for that reason you will see that there is a kind of strip at the edge for every odd movement, and that is because we're working in pairs of bytes, and so we don't have enough bytes to draw both parts in this case. So because of that, and to simplify the routine is always working in pairs of bytes, and so sometimes there is one byte missing. Now, one option to solve this would be to have two versions, one for when the sprite is partially off screen and when it's fully on screen. That is a good idea, but for today's example I'm using the same routine for both. Now, as well as using stack misuse to speed up the routine, we're also doing another thing. We are actually using page flipping. We've got two screen buffers. One is being shown to the user while the other is being drawn. We then swap them over, and then we start drawing that one and then swap them over again. So every other frame we're flipping them over. There are two screen buffers in memory. Now, the screen is approximately 16 kilobytes. It's actually 12, but the layout of the memory means that it's there's a lot of spare space on the CPC screen, so it's using almost all 16K of the bank. But as I say, these two screen buffers are at C000 and 4000, and so we're swapping them as over. Now, it's perfectly possible on the Amstrad CPC to have the second screen buffer at 8000s instead of 4000, which I would in most cases recommend you do. That's what Chibi did, and the reason I recommend that is the 4000 to 8000 range is actually the one that can be page flipped on a 128K system. The problem with using the 8000 range, and why I'm not doing it for this simple example, is that range is used by the operating system and it's also used by the default stack pointer. So if you use that range for your screen buffer, you're going to lose the operating system, and that's going to make it impossible to use disk operations and also firmware functions if your software relies on them. Chibi was restoring that disk function data. It was resetting the operating system essentially when it needed to reload, but of course that's a lot more complicated. So that's what we're doing today. That's why we're using that memory layout. Let's go over to our code and let's see what is actually involved in it. Over we go. Okay, so I'm not going to go over the basics of how this cropping routine works and the code for drawing it, because we went over that last time. If you need to know it, please see last time's example. Now, the first thing we do need to look at is the way we're setting up our screen. Now, our screen is not 320 by 200, it's 256 by 192, so closer to a Spectrum screen, things like that. So this is something I wasn't a fan of doing originally. Chibi was 320 by 200, and that's because the CPC screen is big and I wanted to use full use of it. But generally speaking, I would recommend you reduce the screen size to 256 by 192. Two reasons for this. Firstly, you have compatibility with other systems if you're looking to port. Most systems are based around 256 by 192, then far fewer are larger than that. So it gives you more portability. The other thing is the memory layout. It's far easier to move across the screen. If you are in a 256 widescreen, you can only update the L byte rather than the HL byte of the HL pair, so you will end up with faster code as a result. So generally speaking, yes, I would recommend you do it. Now, to change the screen settings, we have to send a bunch of CRTC values to the screen hardware, and it's register 12, which is 30 here, which defines the screen start, and it's these two bits here. 30 will define the screen to be at C000 here. So that is our default screen, visible screen for the Amstrad CPC, and we're transferring all these registers just here. This sequence here is sending these register values. Now, we have a function here called flip screen base. This is doing the page flip. As I say, the visible screen you're seeing is not the one that is being drawn to. There's a second screen which is being drawn to, which is elsewhere in memory, and it's this flip screen base function which is handling the flip, and it's also handling the reconfiguration of the software to define the new screen destination for the calculations. So here's the flip screen base. We're loading in the current screen base from screen base +1. This is self-modifying code. I'm modifying the values in the get screen pos function, I think it is. So we're loading it in from that modified value here. We're then backing it up into AF, and the first thing we're going to do is we are going to set that screen base, which was the screen that's been drawn to be the visible screen. Now we need to shift the bits, so we're doing an RRCA here. We're shifting those bits, so we're effectively converting the value C0, which is the top byte of the base of the screen memory, to 30, which is the format that this register wants. We're then loading BC with BC-OC, which BC is the select register of the CRTC, and OC is the register we want to change, register 12. We then out that selects our register that we want to change. We're then increasing BC to BD, and we're then using that port, which is now the value port, and we're outing the value that we've calculated from our screen base. So that is defining the new screen base of the visible screen, and as soon as we do that, the page will flip and we now see what we've been drawing. Now, if we were going to be super accurate, we would do this during VBlank, because then the user will never see anything that's occurred. This version isn't doing that, it's just doing it immediately, so there is the possibility you might see some screen tearing, things like that, but for a simple example here, it was fine. Just bear in mind though that, as I say, it's technically speaking, I suppose we should do this in VBlank. Okay, so that has defined the screen for the hardware. What we now need to do is define the new screen base for the software, so that the drawing goes to the new buffer, which was the old visible screen. Now, in this case, we are using C000 and 4000 as our screen bases, so we're XORing the top bit of that byte, and that will flip between C0 and 40, and so that will toggle between our two screen bases. Now then, what we're doing next, we're storing that in the screen base +1, which is part of our calculations, but what we then need to do is we need to alter the get next line function. Now the Amstrad CPC screen is a little bit annoying. Like a lot of screens, it's kind of interlaced, so 8 consecutive lines have one simple mathematical calculation to move down a line, but then the next jump is much more complicated, and on the Amstrad CPC you basically need to wrap around back to the top of the screen memory. And so what you do is you have a bit within the memory address of the screen destination that you need to test, and then when that bit flips, you then need to add this value of C40, I think it is. It varies as well depending on the screen width, but the bit we need to test and the condition that we need to apply to that test, so is it 0, is it not 0, things like that, vary depending on the screen base, which is quite annoying, but that's the way it is. So if we have got a screen base of C000, we are going to need to use this calculation. If we've got a screen base of 4000, we're going to need to use this one. And I've also left in the code for if the screen was at base 8000. And so the tests we're going to need to do are going to vary. If it's at C000, we're going to test bit 7 and jump if bit 7 is not 0. Basically, if we're still writing to memory within the C000 range. When we overflow back to 0 and we would start writing at the quadruple 0 range, we've overflowed and we need to do that correction. If the base is at 4000, we need to test bit 6 instead, and we need to jump if it's not 0. But if our screen base is 8000, we need to test bit 6 and jump if it's 0. Now these bytes here are the byte code of these commands, so I've manually assembled those using just a lookup table and worked out what bytes should be in memory, and we are modding these into the code. So this is self-modifying code, and those bytes will replace parts of these two lines here. So we will replace the bit 7 with the correct bit, and we will replace the kind of jump relative we're doing here with the correct jump relative for our screen base. So this is self-modifying code. It will only work if the program's running in RAM. If your program's running from a cartridge on a CPC, it won't work. So that's a limitation there, but this is the fastest way of doing things. Self-modifying code, fewer conditions means faster. So that's what we're doing here. Now, it was C040 for this screen size, so we add C040 to correct our screen size. It's C050 if the screen is the full 320 width, but as I say, that's what we're using here. So that is being self-modified to handle the new screen base. The other thing that is being modified is our getScreenPos function. At the very end of our getScreenPos function, we are adding the screen base and also the X position to our VRAM destination. And so here we're adding C0 because our screen base is C000, but if our screen base is 4000 or 8000, we need to add a different byte. So we're modifying that in there as well. So that is how we're handling our page flipping. Now let's start looking at this weird concept of stack misuse, or stack abuse if you prefer to call it that. Now what this is, as I say, where we use the stack pointer instead of as a temporary store, we use it for some other kind of operation. Now in this example I'm using it in two ways. I'm using it to clear the screen quickly. I'm also using it to read the sprite data quickly. So we're using it in both kinds of ways, once for reading and once for writing. Now if we want to write using the stack pointer, we will use lots of push commands. Now every time we do a push command, the stack pointer moves down in memory. So this to use this, what we need to do is set the stack pointer to the end of the range that we want to fill. Actually at the end of the range +1, because when the first write occurs, the stack pointer will move down by 2. Okay, so what we're doing here is we are calculating the destination we want for the end of the range to fill. So we're loading in the screen base here into the accumulator, so that would be something like C0. We're then adding hexadecimal 40, which is effectively we want to move to the end of that 16K range, and so adding 40 has done that move to the end of the range. And then we are loading HL, so H is being loaded with that value, L is being loaded with 0. And we're loading DE with the pair of bytes that we want to fill the screen with. And here I'm using FFFF. And that is filling our screen with red. And that's why our Chibi-Co is inverted. It's an XOR sprite, so it's inverting. So our clear screen routine is going to do all the dirty work for us. Now, at the start of this, for simplicity, if you're using stack misuse, the best thing to do is to disable interrupts. We're using the stack for fast reading or fast filling of data. And that means that the stack probably can't be used for anything else. And specifically, we can't do any calls and we can't do any pushes or pops for anything other than the stack misuse itself. Now, interrupts are, of course, a call, so we're disabling them. There are some clever things you can do if you make your stack, your interrupt handler, aware that stack misuse is going on and switch to a shadow stack and do some other clever things. You can get around this. Chibi did, and I've already created a tutorial, I think in the multi-platform series, where I covered how you can write an interrupt handler which will cope with stack misuse and will compensate for it. So in the case of filling memory, it probably doesn't matter until the last byte, and in the case of reading memory, as long as you swap back the data that is in the DE register with the data on top of the stack, you probably won't corrupt anything if you do it right. So, but as I say, this version is simple, and if you're just getting started with stack misuse, just disable interrupts as soon as you start, before you start using the stack in that way. Okay, we're then zeroing IY, and that's because we want to transfer the stack pointer to IY, but there's no direct command to do that. So IY now contains the correct stack pointer. And at the end of our code, we will load IY back into the stack pointer, restoring the stack pointer. Between these two, we can't do any calls, and we can't use the stack for any normal things. Now, HL, when this routine starts, is the end range that we want to fill with our value, to fill the screen, clear the screen. So we're now transferring that to the stack pointer. So the stack pointer now points at the end of our range, and then we're going to repeatedly push DE to fill the entire screen range. And it's very fast, push DE, faster than any other data writing command. That's the point. Stack pointer commands are faster, about twice as fast as normal commands that you could use to do the same job. So that's why we're doing them. The other thing we're doing here is something known as unwrapping a loop. Now we need to push DE to fill 16 kilobytes, so about 8,000 times. Now we could do a loop 8,000 times, but all of those loop commands, all of those decreasing our loop counter and checking the loop counter, it's going to be slow. So we do something known as unwrapping the loop, which is basically where instead of having lots of loops, we have lots of raw commands. So what we've got here is a sequence of push DEs here, and this is the equivalent of transferring 64 bytes in one go. So all of those push DEs will do 64 bytes. Then we're then repeating just using our B counter, and we repeat that just 256 times, and that will fill our entire 16K screen. So that's what we've done there to speed things up even further. If we didn't, then the push DEs would give a slight benefit, but not much. But by unwrapping the loop as well, the two combined make this extra fast. This is a very fast loop. Now, if we were going even more extreme, we could make this more optimized, because as I say, the area we're filling is 16K, but the visible screen is actually only 12. So we could have optimized this further and only filled the visible area. But for simplicity here, I'm not doing that. So I'm actually filling the entire memory area there, but it's good enough for here. So that's how we're using Stack Misuse to clear our screen. The other way we're using Stack Misuse is the actual drawing of our sprite, but rather than for drawing the sprite, we're using it for reading the sprite. And the reason for this is after each line of our sprite, we need to recalculate the VRAM destination. So my thinking was that rather than using it for writing, we'll use it for reading. The other thing is it does make for a nice simple example of how to do it. Now we're doing things a bit differently here. Rather than using IY for our value here, we're loading the stack restore value, the correct value for the stack, via self-modifying code. So we're storing it using this calculation here, and this is being restored down here. So this 0 that we're loading into the stack pointer here, when this command actually executes, will be the correct value for the original stack as calculated by this line here. So that's how we're restoring our stack. Again, we need to disable interrupts when we're reading, because our interrupt handler, we're using the firmware 1, it's not smart enough to cope with this. And then we've got our transfer routine here. Now, rather than pushing data to the stack to fill areas, we're this time popping data off the stack to read it. So this time it's working in the same format as the original one. Every time we pop, we read 2 bytes starting from the beginning of the range. So we're reading our bitmap data. So we read 2 bytes and then we are writing one to the screen here and writing to the other here. So we're doing 2 screen bytes in each loop iteration, and that's why at certain positions, because we're working in pairs of bytes, we don't have 2 bytes read in here, so 1 byte is missing, and that's why you've got that red strip at the left hand side of the screen here. You will see as I move every other movement, 1 byte disappears. That's because we're working in pairs of bytes here. As I say, the easiest solution to this would be have 2 versions of the code: Stack Misuse fast version for fully on screen, slow, more complex version for partially off the screen. But that's not what we've done here. Now, at the end of each line here, we have a get next line routine here as before. Now, again, if we are partially off the screen, we are having to do some clipping here. So what we're doing here is we're loading HL with the amount that we need to skip as parts of the bitmap have been clipped. So we're then adding that to the stack pointer here and then transferring it back. And this is allowing the stack pointer to be updated. So we're skipping over any bytes as needed, again, wasting a little bit of that performance. This isn't really that effective if the sprite is partially off the screen, but it's an example. So I've shown an example of modifying the stack pointer with Stack Misuse. But as I say, I think I would recommend you just use a conventional version that wasn't using this kind of trickery if you are using a partially clipped sprite. But there we go. So that's how we have modified this code, how we've added these extra tricks to allow the code to be more efficient and use the stack in this tricky way and get some extra performance. Now, as I always say, I certainly wouldn't recommend this as you're getting started. If you're just writing your game in the beginning stages, just use simple sprite routines. With Chibi Akima's, what happened for me is I had a proof of concept very early on where there were objects moving and I could shoot them. It looked terrible and the frame rate was about 1 frame a second. As the game started to get more mature and it started to look more like a viable game, and I added things in like sound and the special interrupt handler graphics that allowed for more colours on the screen, the game started getting slower and it became worse, and at some point you will start to need to try and optimize it enough to get the game fast enough to be viable. And it's at that point you're going to want to start looking at things like this. What can you do to make the game as fast as possible? You don't want to make your programming as complex as it can be in the early days, because you'll probably struggle making the game work at all. Once you've got the game working, but it's not as good as it could be, or you're not happy with it, start to use these kind of tricks to make it faster. So, as I say, bear them in mind, use them if you need them, but don't feel you need to put them in just for the sake of it, because the important thing is you finish your game and you get it working at all. So don't make it hard on yourself in the early days. Anyway, hope you've enjoyed this, hope you found it interesting. As always, you can go to my website, you can download the source code, the build scripts, and you can use them in any way you want. And as I said as well, I do have some other tutorials on Stack Misuse if you want to see more, including clever interrupt handlers that work even with Stack Misuse in play. Thanks for watching today, and goodbye.